Okay. Yeah, so I'll talk today about reinterpretation in high-energy physics and particle physics in general. So this is just the README of the talk repository. You can find it linked in the Indico, and it will be purely notebook presentation. You can follow along on the Binder Hub. If this doesn't work for you, you can simply run this locally as well. Just clone the repository, and you have to install the requirements, but that's only a few. So it should work for everyone. Yeah, if you have questions about that, you can just ask in the Slack. All right, lost my Zoom window. There we go. So then let me get right into it. So I'll present the implementation of a reinterpretation method that we have developed, and I want to distinguish between the two. I'll come back to why at the end. But basically, what we're trying to do is perform histogram-based reweighting, depending on differences in kinematic distributions in certain decays. And the library is built around PyHF. So for people who don't know PyHF, I'll give a short introduction in a second. And for people who get curious about the method, there's a paper that we've written. It's online. You can check it out here afterwards. So the plan of today is going to be we measure some thought-up decay, A to B, C, D decay. I came up with that, and we kind of construct a simple analysis for it, do statistical inference, and then I'll show you how easy it is to do reinterpretation if you have the right tools and the necessary information. So the first step is to simulate some signal data, and we assume that the signal is distributed normally in some kinematic degree of freedom Z. So for simplicity, let's assume that decay only has 1. And this is centered around a mean of 4 with a sigma of 1.5. And you have some exponentially decaying background with a scale factor of 5. In addition, you say, okay, I expect 10 times more background events than signal events. So we simulate 10,000 signal events and 100,000 background events. And on top of that, we, of course, need to also simulate our detector response, which we just model here as accepting 10% of the events at random and smearing out our kinematic degree of freedom with a sigma of 1. So we can do that very simply. So we define a mean of 4. We have our normal distribution. We have our exponential distribution. We have a function that simulates our detector and basically gives us back the smeared kinematic degree of freedom, the ones that are accepted, and for the same samples, the true value, so the generator level value, basically. We can execute that, just takes a second. And then you say, okay, we decide our reconstruction variable after considering detector effects. So we call this X now. This is like the smeared version of our kinematic degree of freedom after it passes through the detector, which we model as kind of this transition function. And we say this kind of distinguishes our signal and background distributions well in the region from 0 to 10, and we choose this as a fitting variable as well. So we define some binning from 0 to 10, 9 bins, and we kind of throw out all the events that lie outside this range and bin our signal and background. We can have a look at what we created. So you see in green, the signal, in dashed is the true distribution. It's a normal distribution centered around 4. And in the solid line, you basically see the measured values that we get. So you see a smearing that happens through when the events are passed through the detector. And you have the same for the background, right? So it's just this exponential decaying function. Okay. So now we have kind of our Monte Carlo templates. So the next step is to get some data from our detector. And I didn't have time to really construct a real experiment for this, so I'll do everything with simulated data. But let's say that our true signal is distributed not with a mean of 4, but with a mean of 5. So we actually, when producing the Monte Carlo, we made a wrong choice. We made a wrong assumption. And in addition, there are actually twice as many signal events as we expect. So there are these two differences that we want to incorporate into our real data. And this can be a true situation, right? So you never really exactly know how to model your signal. And we do exactly the same steps as above for the Monte Carlo, just now for the signal. So we have a true mean of 5 now and a scale factor of 2. We generate some signal and background samples, pass them through the detector, histogram this, and then kind of create our data as the sum of these histograms, where we introduce the scale factor here. So let me run this. Okay, so now we're ready to do inference. So for people who don't know PyHF, it's kind of the hist factory implementation in Python. It's become a very common analysis tool for various collaborations. And very simply broke down, it does the maximum likelihood estimation. So the likelihood in a very, very simple form looks like this. So you have, for some observed event counts n, a Poisson kind of data likelihood, which compares the observed data to some expectations nu, as a function of unconstrained parameters eta and constrained parameters chi. And constraints in the frequentist language are imposed by incorporating auxiliary data in your likelihood. And the number of expected events are calculated. Basically, you have some nominal nu naught, and you have some multiplicative modifiers kappa and some additive modifiers delta. So these can kind of shift your histograms up and down, or bin-wise, or sample-wise, or all over. So you have many different options there, but the basic features are either multiplicative or additive. So what we now do is we construct a very, very simple statistical model. So we have a signal, a background, we add Poisson error for our background, and just as an aside, we use cabinetry here for visualization because it has a nice feature of also kind of calculating the correct uncertainties for us. So this is how you then construct a very simple model in PyHF. So you give it the signal histogram, the background histogram, and background uncertainties just as square root of the histogram. And then we can look at this at the prefit plot. So in blue, you have the background, in green, the signal. These hashed regions are the uncertainty, and the black points are just our data points, right? And we already see in the pool plot that we're very far off, right? So we have a very, very strong deviation, and this is expected, right? Because we made not just the wrong mean assumption, but also the wrong scale assumption. So now let's see if things look better after we do a fit. So you can also use Cavendish for that, but you can also just do this simply in PyHF. And we see the fit results here. So the mu here is the signal strength, and we see, okay, actually we get the signal strength of 2 correct. So this is nice. But either so these background uncertainties are bin specific factors. So for each bin you get one kind of parameter here. That's you can already see the pools, right? So you can see the lower pools on the first 2 bins and very high pools to upper values on the last 2 bins. And you can see this in the post-fit distribution as well. And this is now the effect in action that we have a shift in our signal distribution. So you see this lower kind of drop here and this bump at the last few bins. And now you can say, looking at this just at this post-fit distribution, would you trust a fit that looks like this? So personally, I would be a bit skeptic. I would say, okay, given the uncertainties, the pools here are too far. So what do we do now? So, I mean, we got the scale factor correct, but yeah, I don't know. Trusting a fit result like that looks like this, maybe not. So to make things a bit better, we decide that the signal PDF might not be the correct one. So it would be nice to allow for some more freedom in that PDF. And we allow for kind of a modification parameter m. So this is our new mean. Keep sigma the same for simplicity now, but our PDF is going to be so for our kinematic degree of freedom given some parameter m. And in reality, there is no easy way to do this. So once you have a statistical analysis, the thing that you'd have to do is pick an alternative value for m, generate new Monte Carlo samples, simulate the detector response on top of each of these samples, and then redo the statistical analysis. And repeat this until you have found a good value for m. So this is not only computationally very expensive, but also from a point of view of your time as a physicist, this is going to cost you a lot. So what about a better way? And this is where our reinterpretation method comes in. So just to summarize what we did, so we calculated a number density n of x in our reconstruction or fitting variable x. And we did this for signals and backgrounds, and we stacked these, and that's what we compare to our data. So this is the idea of template fitting. And when we produce the Monte Carlo samples, we usually make a choice. So we choose a theoretical prediction, sigma of z, I call it here. So this is basically, could be a differential branching ratio, for example, but it's the scaled PDF of your kinematic. And in like kind of a schematic way of showing this, so you can have different distributions for your theory, right? So you can have either say model A in blue or model B in red, and depending on which one you choose, you will end up with different distributions in your reconstructed variable. And these are connected by the simple formula here. So you have your theoretical distribution, and then we've seen this object before. You have this conditional reconstruction selection efficiency transition function. So it's kind of a folding operation. And you do this folding, and you have to scale by the correct luminosity, sum over your bins in your kinematics, and then you end up with this number density in your reconstruction variable for the correct luminosity. And kind of for further convenience, we can then kind of group these objects into a joint number density n of x and z. So this is just going to be the combination of these, so multidimensional number density. So, okay, so this is how we go from theory to the reconstructed distribution. But actually what we have is a distribution in A, and what we want is a distribution for our model B. So this is one more additional step. So how to kind of go from one to the other. So say what you want in the end is your bin yields for some alternative theory B. You do the same reconstruction as we just did above for sigma B here. And then you can introduce two factors of sigma A. So you can introduce one in the numerator, one in the denominator, and you can collect the first three terms here into a joint number density underlying theory A, and you can collect the rest into a set of weights. So this is just the ratio of these two distributions. And basically, bin integrated kinematic predictions, so the ratio of that. And the convenient thing about doing it this way is that this object here, I will show you in a second how to construct it, but it's very easy to do, right? Because as an analyst, you have access to the Monte Carlo samples, which have the information about the reconstructed variable x and your kinematic variable z or multiple kinematic variables. So this is easy to compute for you. And this kind of already hints now at the fact that if you have the statistical model plus this joint number density object, then you can compute alternative distributions in your reconstructed variable, and you can perform the inference again with a new underlying theory. And this is a very simple operation. So this is a very simple matrix operation to obtain a new template and then just do a simple fitting operation. And that's a very, very simple way of doing reinterpretation. So let's apply this to our example. Before I do this, just kind of since we're talking about implementation and packages here a lot, how we incorporate this into PyHF is basically, if you remember, the expected number of events, how they're calculated. So you have these multiplicative and additive modifiers. So we basically exploit the fact of multiplicative modifiers. So for each bin in our reconstructed variable, we have basically then the ratio of our expected number of events underlying theory B over the expected number of events underlying theory A. So for each bin, we basically shift our histogram by this ratio. So this is the simple implementation of this. Good. So coming back to our example, we now have to define sigma A and sigma B. So this is step number one. And our null hypothesis, sigma A, is the theory that we used to construct our Monte Carlo samples in the beginning. So this is a normal distribution with a mean of 4, sigma of 1.5. We've seen this. Now, for alternative hypothesis, we want a free-floating parameter m, so we want a free-floating mean. And in addition, we already know that we expect more signal events than expected by theory A. So we can incorporate a scaling factor of 2 now into our theory here. So this is going to be our new alternative model with one additional free parameter. And kind of only relative scaling matters here, right? So between these two theories, because they are only used to construct the weights. So what we then do is we simply define these two formally. So I don't have to explain this again. I think it's just normal PDF mean of 4 and a free floating one with a scale factor of 2. It's very simple. And step number 2 is to create this joint number density object. And for convenience, we implemented a function in Redist for this that constructs this out of the samples. So it takes the reconstructed information, so our X samples as a first argument. And this is one-dimensional because PyHF basically flattens everything out to one dimension. So this is always going to be one dimension. Whereas the kinematic information, which we enter here as a second argument, is entered as a list because you can have multiple kinematic degrees of freedom. So this is allowed, right? So you can have momenta, angles, etc., etc. And then the same for the binning. So the third argument here is the binning of our reconstructed variable x, and the second or the last argument here is the binning of our kinematics, again as a list because you can have multiple kinematic degrees of freedom. And here, for simplicity, we just choose the same binning as we used for x as well. We don't want to overcomplicate things. So before we look at what we just created, we can actually create this modifier kappa itself, so the object, and we have some very simple visualization for that. So the modifier itself is internally just initialized as a class instance of this modifier object. And in addition to the things that we already mentioned, it takes a list of the new parameters that we're going to introduce. So we define a dictionary for this new parameter and say your theory friend tells you m of 3.5 is a good choice. Yeah, everyone can be wrong sometimes. Actually, we know it's 5, but let's say we trust our theory friend and put in an initial value of 3.5, but we're a bit skeptical, so we have some wide bounds on this parameter, and we leave this parameter unconstrained. Now, to define our modifier, we give it this dictionary, our theories, this joint number density object, and the kinematic binning, and we can give this thing a nice name, very M in our case. We run this, and now we can actually look at what we created. So first, we can look at the distributions. So on the left, you see null and alternative distribution, so the null hypothesis in blue. So this is simply normal distribution centered around 4. And alternative distribution in green, it's a normal distribution centered around 3.5 now. So we have this parameter, so we could change it to 5, for example, and we see this distribution changes. And on the right-hand side, you then see the weights that will be applied. So this is simply then the ratio of these two histograms. Now, the weights are applied to the joint number density object. So this we can also plot. And in our case, it's basically simple two-dimensional matrix. In the reconstruction bins, this is our x, and kinematic bins, this is our z. And on the z-axis, you have basically the events thrown into this. Now, you can already see you have this like nice smeared distribution because we have our detector effects incorporated, and you have a lot of empty bins. And empty bins here usually. This is a bit scary. We don't want empty bins because of statistics. But in this case, it doesn't matter, right? Because we're simply, we're applying weights and then summing over the rows. So it just matters that the rows are not empty. And yeah, perfect. Thank you. Yeah, so then we get this object. This is kind of the main object for interpretation. So then basically what we can do is we can add this modifier to our PyHF model. And this we do with providing a specs dictionary. We give it, we give the actual modifier in the spec a name. The type is now the name of the modifier that we provide above. And the expression is the name of the custom function, the custom weight function in the global namespace. So per definition, this is just the modifier name plus the weight function. And then we can specify where in the statistical model we want to apply this, so which channel, which sample. Cool. And then in the end, if we add this to our model, we can print out the parameter names of our model now. And we see that M is here. So we can now fit for M. So let's do this. We can perform a new fit and plot the results. And we already see from the fit results here, we get the correct value for M, even though we put in the wrong value at the beginning as initial value. We get the correct scaling factor, which is around 1 now, because we already introduced this factor of 2 before. And if we look at the pool plots, they look a lot better than before. So we kind of match our data much better. So in the end, the cool thing here is we have the same statistical model, but we managed to squeeze out more information from it. And this is something that we can do with a lot of our particle physics results. So once you publish something, this is not the end of the story, or it shouldn't be. So people might find uses for your analysis that you didn't even imagine. So it's nice to have these things published. So just as a quick note, what I haven't shown today, you can save and load these things. So we have a save and load function to JSON format, so this can be distributed as well. Except for the functional form of the theories themselves, because this is not easily put in JSON format. We allow for correlated parameters. This is also not something that's initialized in PyHF. So you can do in a new parameters dictionary have multiple parameters and a covariance matrix, and you can combine models as well, which is nice to reduce uncertainties for theory parameters that are maybe have different sensitivities. Good, that brings me to my summary already. Redist is, again, an implementation of the presented reinterpretation method, which allows for fast reinterpretation with minimal additional information. And this enables bias-free inference on shape-changing parameters and theory parameters. And it only requires publishing a statistical model and a joint number density object. So this is something very easy to do. And I believe collaborations should provide this information to allow reinterpretation outside of collaborations for theorists as well. Redist is built to work with PyHF, but the method is much more widely applicable, and it would be great to see this also with other tools. So if you're interested in applying this, feel free to contact me if you need any help. We've seen quite extensive discussion about ZFit with how to implement custom PDFs. So it should be very easy to do that within ZFit as well. And then just before we turn to questions, yeah, I have a small bonus thing for people who love Bayesian inference, so you can calculate posteriors in your own time if you want to. And with that, I'm done and happy if there are any questions. I'm happy to answer or try to answer. And thanks a lot.
Okay, thank you. Yes, any questions? I want to leave the floor open for anyone from the audience before I ask. Actually, what I want to ask about is combine, because the histfitter model has been widely used in Atlas and much less so in CMS. CMS has its own tool, combine. Like you said, that this is more widely applicable and it can be used with other tools like ZFit. Would that enable optimization of CMS analysis if a lot of work has already been invested in developing combined cards? You know, the whole configuration is all in combine, and it's a big thing that you don't want to port. Any suggestions for that?
So sorry, what was the actual question?
Oh, the actual suggestion is, suppose that someone has a big complicated fit expressed in combined cards.
Yeah.
How would you, let's say that they want to apply this method, how would they get from there to something? Or would they have to re-implement it? If not in PyHF, would they have to re-implement it in ZFit, or is there some way to like approach the users who have already invested quite a bit in Combine?
Yeah, so I think in the end they probably have to re-implement it. But the implementation of this is actually very simple. So it's a simple matrix operation, right? So if you look at the actual repository for this, it's very small. So in the end, if you have this object, it's very simple to kind of calculate new number densities. So I think I mean, or in ZFit you can do this with custom PDFs, but I think it always boils down to having this object, creating this object is maybe the one thing that CMS would have to provide in addition to the combine cards, and the rest should be quite straightforward.
Okay. We have two hands. I saw Alex's first.
Yes, hi, Lawrence. Thanks for the nice overview. I've been wondering, could you, in principle, replace an entire bump hunt with your method, like what we currently do in new physics searches? If I say I have a model with one free parameter, and what we currently do, right, is we simulate for every model parameter a different Monte set, and then we search for this with the bump hunt. It seems like you tackled this problem as well.
To some degree. So it works as long as you have enough samples. So I think that this here illustrates it already quite well. So say your original samples are distributed like the blue curve here. So you're gonna, at some point, you're gonna end up with regions that have very, very little samples. So if you want to then do a bump hunt at kind of high Z here, then you will see, so here already you see at the last bin, you already scale up your events by a factor of 12. But now if I would go, if I would make this even higher, then you already see, okay, I scale up my events by a factor of 40 in the last bin. And this is where you have to start to be a bit careful. So I suggest when you apply this to an analysis to have a cutoff at some weights. So in principle, it's possible to make the answer a bit short, where if you have enough samples in all of the regions that you're looking for.
Okay.
Does it answer the question?
Yes, it does. Can I have a follow-up?
From my...
Yeah, just follow up and then Nikolai's question, then we'll move on.
Yeah. Have you tested this on this ability for how small the bins can be? For example, at Build 2, as you know, we have a 10 GV range mostly to search for, and now we search for signal windows of 10 MeV per signal window. Would this still be stable with this method?
Yeah, so actually what I'm currently working on is I'm searching for resonance in one of our analyses, and this is possible as long as, again, you have this condition fulfilled, that you have enough events in that region, and that your kinematic bins here are fine enough. So if you introduce kind of very, very sharp distributions here, you want your kinematic binnings to be quite fine to kind of resolve these resolutions. In the end, you're still limited by the resolution of the experiment, of course, but choosing your kinematic bins very finely is not an issue. So this you can do as fine as you want. As we said, having 0 entries in some of these bins just means the weights are not applied, but it doesn't give you any limitation.
Thank you.
Okay. Now, last question from Nicola.
Yeah, not really a question, just quick comment on this PyHF and combine thing. I heard there is some kind of converter out there, but I'm not sure like how complete this works. You might actually know better than me. So I'm not sure how compatible the combine and the hist factory models are. I think there are some slight differences in terms of what things you can do, but overall it seems more or less the same model I had At least that's what I got from the discussions.
Yeah, yeah. One thing is that PyHF is purely binned data, and combine might include some non-binned data, maximum likelihood. So you can't always convert it. I suppose if you were within the set that can be converted, then you could use the redist PyHF bridge after conversion. Maybe is redist compatible with unbinned fits?
Yeah, so the redist itself, the implementation is not. So the implementation is purely focused on PyHF, which is purely binned. The method itself it is, right? So if you look at the paper also, I presented these formally here in a binned way, but you might as well just replace these with integrals and have this in an unbinned way. So it's applicable to continuous distributions as well.
Okay.
Well, I mean, this detector of resolution modeling might be quite difficult to do completely continuous, right? I mean,
yeah. There you'd have to do some interpolation maybe.